Okay, so now I want to look at the energy momentum for vector. So let's so we've got P mu equals to E. And just for the first part of this lesson, I'm going to keep the speed of light. Okay, so I'm not going to set C to 1. So we've got P and we've got C. Now, you know that if we take P mu, well, these indices should be summed. There's one upper index, one lower index, and this will give us something that is Lorentz invariant. Well, if I work out what this is just E squared minus C squared into P dot P. And this is Lorentz invariant. So it doesn't matter what Lorentz frame I work it out in, I'll get the same answer. This is something that's invariant under rotations, and it's invariant under boosts. And well, it turns out, I'm just stating this result, that this is equal to m squared c to the 4. So if I just rearrange this slightly, I get the following equation. E squared is equal to m squared c to the 4 plus c squared p dot p. This is quite a famous equation in special relativity. It's an equation that you might be familiar with. And well, I just wanted to make contact with it. If you set the momentum equal to 0, so you consider a particle that is at rest, then this equation simplifies even further to E. It tells you that E is equal to mc squared. That's a very, very famous equation. It's profound. It's telling you that energy and matter are equivalent. This is maybe one of the most famous equations in physics. I've seen it written on bus stops. I've seen it written on walls. In the bathroom, people have written some graffiti which says E is equal to mc squared. And I doubt that all of these people are physicists. So this is, in fact, an equation that's known to everyone in the public. And, well, we make contact with it. It's related to the fact that P mu is a Lorentz invariant. Okay. So we've spoken about 4 vectors and how they transform. And the basic equation that we wrote is this one. We said, consider the position 4 vector, which was the time, and x, y, and z. And we said that if we boost from the original frame to another frame, which is moving, and moving along the x direction, so it's a boost along x, we have already studied this particular Lorentz transformation, this boost. And this is how it looked, t, x, y, z. Now, I might want to write this in 4-vector notation. So what would I do? Well, I'll have x primed mu is equal to, now I have some matrix and this 4-vector x mu. And remember, whenever you have a matrix multiplied into a vector, there's a sum here. So for example, t prime is equal to, and it's a sum of 4 things, it's cosh phi times t plus sinh phi times x plus naught times y plus naught times z. So the way that this is written, we write the matrix as lambda mu upper, nu downstairs, and then we've got x nu. So by the Einstein summation convention, we should sum on nu. And I want you to think about this very carefully, that sum on nu is the sum that naturally appears when we multiply a matrix into a vector. So think about that. This is a good equation to spend some time thinking about. Think about why this matrix equation becomes the 4-vector equation that I've written. Just to make things more explicit, if, for example, we study lambda naught naught, well, this would be cosh phi. So the indices mu and nu on the lambda go over 0, 1, 2, 3. So we don't start from 1, we start from 0. What would lambda 0, 1 be? So take a minute, study the matrix. So what would lambda 0, 1 be? Did you get sinh phi? If you got sinh phi, that's perfectly correct. Let's do one more. What is lambda 3, 3? Look at the matrix. Yes, that's 1. 3, 3 would be the last entry because it's row 0, row 1, row 2, row 3, column 0, column 1, column 2, column 3. So the 3, 3 entry is the one sitting as the bottommost and rightmost entry in this matrix. Well, this is very interesting. Lambda mu nu has 2 indices. Because it has 2 indices, we would say that it is a rank 2 tensor. So we don't only have 4 vectors, which are things with just a single index. We've also now introduced tensors, which has more than one index. Lambda mu nu, which has 2 indices, is called a rank 2 tensor. We might say it's a rank 2 tensor with one contravariant and one covariant tensor. If we had something with 10 indices, then we would say that it has rank 10. And for each index, you could say whether it is a covariant index or a contravariant index. Now, remember what we said? All of this index notation is being invented to tell you how this object will transform. So everything with a contravariant index transforms in the same way, and everything with a covariant index transforms in the same way. So let me make this point very explicit. We've just said that x prime nu, so I'm repeating the equation, is lambda mu nu x nu. So how does the contravariant index transform? Well, it transforms with this matrix lambda. If I have a rank 2 tensor, so let's say I've got t primed mu nu. So I want to work out what is t prime mu nu, which is this rank 2 tensor in the new frame. Well, I'll have a lambda mu alpha and a lambda nu beta and a t alpha beta. So under the same change of frame, which we did to relate x prime to x, we find that t prime mu nu is related to t alpha beta in the form of the equation that I've just written down. And can you see that each index, the alpha index and the beta index, have both transformed with this matrix lambda? And that's what I mean when I say that every single contravariant index transforms in exactly the same way. And I would call T a rank 2 contravariant tensor. Okay. Now let's look at S primed mu nu alpha. What tensor is this? Okay, try to say it. Okay. So did you say that this is a rank 3 contravariant tensor? If you did, that's correct. Now, why don't you pause the video and see if you can write down the transformation rule for this tensor? Okay, so you want to relate S mu nu alpha, S prime mu nu alpha to S, let's say, beta gamma delta. Okay, try to complete this equation. Pause the video, complete the equation. Okay, is this what you wrote down? So lambda mu, the first index came from beta. Lambda nu, the second index came from gamma. Lambda alpha, the third index came from delta. So if that's the transformation law that you wrote down, then you got it perfectly correct. This is how this rank 3 contravariant tensor would transform. So we haven't said yet how lower indices transform, covariant indices. So let's state the rule for covariant indices. To do that, we need to introduce something called the Minkowski metric. Okay. The Minkowski metric is a rank 2 contravariant tensor. So eta mu nu. So I can write it as a 4x4 matrix. Shouldn't really call it a matrix, but anyway. So eta mu nu would be given by 1, 0, 0. There's a minus 1, 0, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 0, 0. So that's what eta mu nu would look like. Now, I want you to check this 4-vector equation. So x contravariant index mu is equal to Minkowski matrix eta mu nu, and then contract this with x and a covariant index mu. This is not one equation, this is 4 equations, and you should be able to check that this is true as a 4-vector equation. Now, what does a matrix do? A matrix acts on a vector to produce a vector. Eta mu nu has acted on a covariant vector to produce a contravariant vector. So that's why I don't like to call eta mu nu as a matrix. It acts on a covariant vector and produces a contravariant vector. In contrast to this, look at the equation that we were studying above. Okay, so I'm going to outline that in blue, that blue equation. So here you can see that lambda mu nu, this really does behave like a matrix. It acted on a contravariant vector x nu, and it produced a new contravariant vector x primed mu. Okay, so that's just the reason why I said I don't really like to talk about the Minkowski metric as a matrix. It's because it acts on a covariant vector and it produces a contravariant vector. Good. Please check that this last boxed equation, boxed in black, the last one on the slide, is a correct equation.